So the theme of this series of videos is to explore different techniques for solving problems in dynamics, and so far we have been focusing on kinematics and specifically on derivation of velocities. We have shown multiple techniques. One of them is using relative velocities, and another is the use of direct differentiation of position. In the process, we have also used quite heavily the rotating coordinate frames or rotating reference frames, and solved problems with an emphasis on rigid bodies. So in this video, we are going to following that theme, we are going to take one of the prior problems that has been posted, and we will solve that problem using an alternate method. The problem that we are going to solve is the position of velocity of the position of a point on spinning and precessing gyroscope. We have solved this before, and it can be found in one of the prior videos that have been posted. So the problem goes like this. For the sake of convenience of drawing the system, I'm going to first start by drawing a circle, which is basically going to represent a sphere in a spherical coordinate system, and let's say that this XYZ is a fixed reference frame XYZ, and on this spherical surface there is a latitude and there is a longitude. We have used this concept of latitude and longitudes to draw our unit vectors in a spherical reference frame. So I'm just drawing that to start off the description of the problem. So let's say that there is a bar that is going from O to O prime, and at the end of this bar, that is at O prime, there is a disk that is attached to this bar, and it is spinning. Now the unit vectors, so this bar along with this disk will be represented through a rotating coordinate frame, which is a spherical coordinate frame, and these are the different unit vectors. The latitude and the longitude, or the latitude and the meridian, helps me position a point on the spherical surface. The projection of this bar, by the way, the bar is of length capital R, and the projection of this point, let's say, is O prime, and the projection of this point on the horizontal surface is the point Q, and that Q makes an angle phi. with the positive x-axis in the counterclockwise direction. The bar itself makes an angle theta, and there is an arbitrary point. There is an arbitrary point P on the circumference of this disk. The disk is of radius small r, so this distance is small r. Okay, that is, the radius of this disk is small r, and the angle that this point P makes at an arbitrary instant from the E phi axis is given by the angle alpha. Okay, so the point P, if I explain this one more time, the point P is a point on the circumference of this disk. The point P is therefore going in a circle around this point O prime. Alright, at an arbitrary instant, the point P makes an angle alpha with the E phi axis. By the way, the E phi axis is tangent to the latitude. The angle theta in this problem remains constant. So let me say that theta is constant. It is also given that phi dot is constant, and furthermore, the spinning of the disk about this bar, which is alpha dot, is also a constant, and alpha dot is referred to by capital omega. Okay, so just to clarify the conditions of this problem again, the bar is going from O to O prime. It's of length capital R. On the bar is a disk. That disk is spinning with an angular velocity of capital omega. The bar itself is going around the z-axis with an angular velocity of phi dot. It makes a constant angle theta. So you can imagine that this point O prime is actually tracing a horizontal circle. It's tracing a horizontal circle along this latitude L. We use a spherical reference frame to indicate the location of the point O, and also to formulate the position of the point P with respect to O. So this is O prime, by the way. So a spherical reference frame is being used to locate the point O prime and to represent the location of the particle with respect to O prime. What we want to find is the velocity of P. Okay, and we will use this spherical reference frame, and this is going to be method 2, and we'll be using direct differentiation. You can refer to my prior videos. Now the picture is a little bit clear, so you should be able to see this O prime and P and alpha and so on. So the approach that we'll use is direct differentiation. In one of the previous videos, we have solved the same problem using the relative velocity concepts, and there is also a prior video where we have given a detailed description of the spherical reference frame and how the spherical reference frame is defined. And in that video we have talked about how one can use a latitude and a meridian as an effective way to not only indicate the position of a point on a spherical reference frame, but also to use that to formulate your unit vectors that are used in a spherical coordinate frame. The spherical coordinate frame is a rotating frame, and one of the big benefits of rotating frames is that when you have rigid bodies that have multiple rotations, these rotating frames are very effective ways of expressing this multitude of rotations. So for example, over here the bar itself is rotating, the point O prime of the bar is rotating is rotating along a circle which forms the latitude. So essentially the tip of this bar, or O prime, is rotating or taking a circular path at a particular height, okay, with reference to this sphere. And so that is one rotation, and on top of that there is a disk, and the disk is spinning about the rotating bar, about this rotating bar. So the rotation of the bar is referred to as the precession, and this is the spinning motion, and in all, the rotating bar and the spinning disk is considered as a gyroscope. The fact that theta is a constant is a special type of gyroscopic motion. The angle theta is often referred to as the nutation, and there is, in this special gyroscopic motion, the nutation angle is a constant. So the process that we are going to adopt in solving this problem is direct differentiation, and here the direct differentiation process is easy to formulate because direct differentiation always requires us to formulate the position of a point whose velocity we desire with respect to a fixed point. And here the fixed point is quite evident. It is the origin of the sphere. Okay, so since the origin of the sphere is already very well defined, so then we can come up with the position of the point P and then differentiate it. So direct differentiation requires us to express the position of a point with respect to a fixed point, and here the fixed point is well defined. So we'll say that the position of P, which is Rp, is equal to O prime plus O prime P. Okay, so the vector going from O prime and then the vector going from O prime to P. So the vector going from O to O prime is a vector like this. The arrowhead is pointing towards O prime, and the vector going from O prime to P has an arrowhead that points towards P from O prime. Okay, so now O prime is given by capital R ER, right, and then O prime P is given by now the angle alpha is being measured from the latitude and along the disk, and so if you resolve this vector O prime to P, you will see that one component will be along the E phi direction, and the other component is going to be along the E theta direction, but opposite to the E theta direction. So we will have R cosine alpha E phi minus R sine alpha E theta. So that's the position of the of the point P, and now to get the velocity of P, all we have to do is take the derivative of the point P, right? So that means I have to take derivative of this vector. Now we have to be mindful of the fact that the unit vector triad that we are using here is a rotating triad, which means that the unit vectors, they change their directions, and so because they change their directions, the unit vectors also have a time derivative. Okay, unit vectors by definition do not change magnitudes, so their time derivative cannot have a change in magnitude, but their time derivative can have a change in the direction if the direction, in this case, because the direction does change. So what we'll do is differentiate this with respect to time. So capital R does not change, so R does not have a derivative, but ER does. So ER dot plus the derivative of this term, but R is a constant. Then the derivative of cosine, well, let's first take the derivative of E phi. So cosine alpha E phi dot, and then let's take the derivative of cosine alpha because alpha is changing, so minus R sine alpha, and alpha dot is nothing but capital omega, and then we have E phi here. So we are using the multiplication rule of differentiation, and now we have the last term, so we will do minus R sine alpha E theta dot minus cosine alpha dot, which is capital omega, E theta. Okay, so now what we have to do is we need to figure out what these derivatives are. By the way, this should be R ER dot. We need to figure out what these derivatives are for these unit vectors, and we know that our unit vector triad is such, it's a right-handed unit vector where R cross theta gives phi. So ER cross E theta gives phi, E theta cross E phi gives R, and so on. So the right-handed coordinate system R theta phi is defined such that ER cross E phi gives, or rather ER cross E theta gives E phi. Right. So ER cross E theta gives E phi, and that's the positive sense of cross products. And furthermore, the angular velocity needs to be figured out for this rotating frame. Now the rotating frame is fixed to the bar, that is OO prime. It is not fixed to the disk. Therefore, the angular velocity of the rotating frame is the angular velocity of the bar. Okay, it is, if it was fixed on the disk, then it would have been the angular velocity of the disk itself. Here it is fixed on the bar. So the angular velocity of the bar is basically this phi dot, and phi dot is a vector that is directed in the z direction, so it is phi dot Ez. Okay, and if there was the angle of nutation, if that was changing, then that would also would have to be included, and in that case it would have been theta dot E phi. That would also have to be included if the angle of nutation was changing, but here it is not, so we can make this term equal to 0. Now the problem with this description is that Ez is not one of our unit vector triad, one of the vectors of the unit vector triad. So what we need to do is resolve this Ez and express Ez in terms of ER, E phi, E theta. Now that is pretty easy to do using the geometry here. We see that Ez is making an angle of theta with ER, and so if we take Ez cosine theta, we are along ER, and similarly if we take Ez sine theta, it is going to be along E theta but in the opposite direction. So basically we have phi dot times cosine theta ER minus sine theta E theta. So then the angular velocity is phi dot cosine theta ER minus phi dot sine theta E theta. So that's our angular velocity omega. Next, what we do is we continue with our velocity calculation, and we say that Vp is equal to then R, and ER dot is going to be omega cross ER. We have discussed this before, that the rate of change of an unit vector is equal to omega cross that unit vector. So it is omega cross ER, okay, plus R cosine alpha, and E phi dot is similarly going to be omega cross E phi, minus R sine alpha capital omega E phi, minus R sine alpha omega cross E theta, minus R cosine alpha capital omega E theta. And you see, this is the reason why we formulated the angular velocity vector, because we do need it in our differentiation of the position. So we first do omega cross ER. So omega has two components, ER and E theta. ER cross ER is going to be 0. ER cross E theta is going to give us E phi. So we are going to have minus R phi dot sine theta E phi. Let me just check this. Okay, so getting back to the derivation here, so the first term is R times omega cross ER. Now ER cross ER is 0, and E theta cross ER will actually go in the opposite direction. So theta cross ER gives us negative E phi, and so we have negative R phi dot sine theta, and the cross product gives another negative, so it's going to be plus R phi dot sine theta E phi. Right, and then the second term is going to give us plus R cosine alpha, and we have omega cross E phi. So this is omega cross E phi. So first we'll do R cross phi. So R cross phi gives us negative E theta. So we have R cross phi. So you have negative phi dot cosine theta E theta, and then you have theta cross phi. So theta cross phi gives us positive ER, so we don't need to change the sign. So we will have minus phi dot sine theta, and it is theta cross phi, so it's going to give us ER. Okay, the next line we have minus R sine alpha capital omega E phi minus R sine alpha, and we now need to do omega cross E theta. So omega cross E theta, the first one is ER cross E theta. ER cross E theta gives E phi, so we don't have to change the sign. So we have R cross theta here. So we have phi dot cosine theta. R cross theta gives us E phi. And then we have theta cross theta, which is going to be 0. And then the last term is going to be minus R cosine alpha capital omega E theta. Okay, so these are all the terms that we have generated. So in the last step, we then say that therefore Vp is equal to, now let us collect all the terms in the individual directions and put them together and express the entire vector in terms of a component in ER, E theta and E phi. So in the ER direction we find there is just one component, and that is R phi dot cosine alpha sine theta with a negative sign ER. I'm just checking to make sure. Yes, so this is good. And then the next component that we are going to put together is the component in the E theta direction. So let us collect all the terms in the E theta direction. So we have this term here and we have this term here. So there are two terms, both of them are actually negative. So you have, and both of them have R cosine alpha as a common term. So minus R cosine alpha times phi dot cosine theta plus capital omega E theta. And let me check that. So we have R cosine alpha as a common term, and we have phi dot cosine theta plus capital omega with the negative sign. So this is good as well. And then lastly we are going to put together the component in the E phi direction, and so we have one term here, a second term here, and the third term here. So we have, this is a positive term, this is a negative, and this is a negative term as well. So we'll put R phi dot sine theta minus R capital omega sine alpha minus R phi dot sine alpha cosine theta, and this is in the E phi direction. So this is then the velocity expression. Let me just check if I have the if I have all the terms correctly expressed. Yes, indeed. So this is the velocity then. Alright, and if you double check with what we have posted in the prior video where we solved this problem using the relative velocity approach, you will see that we came up with the same result. In this case, it turned out that the direct differentiation method was not bad at all. It was in fact a compact method. So this is true that in different problems in dynamics or kinematics, you may find one method to be a little more tedious than the other, but essentially all these equivalent methods are applicable. The direct differentiation method is quite helpful in some cases, but keep in mind that depending on the definition of the problem, the direct differentiation method in some cases may require some extra work, because you would have to define a fixed point from which you would express all the vectors, and that may not be there in certain problems. In this problem, fortunately, that fixed point was already available to us because we were using a spherical coordinate frame to represent the gyroscope, and the origin of the sphere was already available to us as a fixed point, and so we used that to express the position of the position vector of P, and then we differentiated it. So that's it for this video, and we will discuss further topics in the upcoming videos. Thank you.